Hello and welcome to the School of Physics and Astronomy at Monash University. In this video I'm going to talk about your future in physics and astronomy. My name is Michael Morgan and I'm the current head of the School of Physics and Astronomy here at Monash. I wish I could welcome you face to face, but this virtual welcome will have to do under the current circumstances. I should also say that there are a large range of videos that you can watch that will take you on virtual tours of our undergraduate teaching laboratories at first year, second and third year, showing some of the facilities available to our students and also tours of our research labs. And so I invite you to have a look at those videos on the same platform in which you've been able to access this current video. So when I say physics or astronomy to many people, this is the reaction I often get, one of horror. How do we justify the study of physics or indeed astrophysics in the current context? Why is it an important aspect of both our culture, our technology, our society? And there are many reasons. So let me address why study physics and or astronomy, and you can study both here at Monash. Okay, so there are many reasons. So let me talk about the fundamental reason, the thing that gets us all excited. Physics and astronomy explores the universe at a fundamental level. But it also provides the basis for many existing technologies. Wi-Fi grew out of the work in radio astronomy. Computers, lasers, optoelectronics, advanced materials, medical imaging, power generation, and many more. Indeed, many of the things that make your life comfortable, allow you to work effectively in the 21st century have their origins in physical ideas, which have been ultimately translated into technologies. The second reason is it provides the basis for many emerging technologies, things that were just in their infancy, things such as nanotechnology, quantum computing that I'm sure you may have heard of, spintronics and atomotronics which you haven't heard of. And let me just say that just as electronics uses the charge of the electron, spintronics uses the spin of the electron, and atomotronics actually uses the whole atom. And these devices are in their infancy and they are expected to provide significant new technologies in the coming decades. So there are many emerging technologies that owe their existence to fundamental science, in particular physics and astrophysics. But another important aspect of studying physics or astronomy is that the skills that you acquire, so our graduates are skilled in empirical reasoning, experimental design, computational theoretical modeling, problem solving, analytical thinking, coding, data analysis and visualization, and written and oral communication skills. These are really extraordinarily important skills and they're necessary for any industry that you go into. Physics and astronomy also provides you with the capacity to deal with uncertainty. Uncertainty is built into the world, it's codified in the world. Therefore, the capacity to deal with empirical data in a meaningful way and to draw deductions, communicate those to a wider community is extremely important. So our graduates are equipped to deal with future challenges, and the sort of challenges that we can expect are in artificial intelligence and machine learning, big data, multidisciplinary and interdisciplinary research, emerging industries such as next generation electronics. The kinds of skills that you pick up undertaking a major or an extended major in physics or astrophysics at Monash provides you with all of these kinds of skills within a very rich environment and allows you to interact not only with academic staff who are leaders in their field, but your fellow colleagues to provide a community of learners. So the next question you might ask is, well, okay, I'm now convinced, I'm sold on it, I want to study physics or astronomy. So why study physics or astronomy at Monash? And there are a number of reasons why I'd recommend Monash, or recommend that you give Monash consideration. So Monash is one of a very small number of universities in Australia that offers the full spectrum of subjects in physics and astronomy from A to Z. So A, astronomy and atomic physics, all the way through to X-ray science, and Z. Well, what's Z? Well, Z stands for zeptoscale physics. That's the scale of 10 to the minus 21 meters. In fact, very short distances mean very high energies. This is actually the scale of the Large Hadron Collider particle physics. So at Monash you can explore everything from observational astronomy, computational astrophysics, X-ray and synchrotron science, biomedical imaging, biophotonics, condensed matter, nanoscience, atomic and laser physics, as I said, particle physics at the septoscale, cosmology, quantum computing, ultra-cold gases such as Bose-Einstein condensates or BECs, and much more. Now this is really important because we do research in all of these areas. We are able to deliver teaching and projects to students at the undergraduate level in all of these areas, so that you will be taught by people who are experts, world experts in their fields, and that provides an incredible excitement and much more relevancy in terms of communicating ideas. So we have minors, majors and extended majors, and there'll be information on the platform, the Open Day platform, that allow you to see what that means. But they're also complemented by outstanding facilities and outstanding equipment. In fact, I would argue that the facilities that we've invested in, both in research and teaching over the last 5 or so years at Monash, place us among the very best in Australia. We've made very significant investments in our teaching and our research. And we're generally recognised within Australia and indeed internationally as leaders in innovative pedagogy, innovative teaching in astronomy and in physics. So another measure of the quality of an institution is in terms of its research. Now, I emphasize research because although many of you may not go on to become professional researchers in the field, having strong research capacity means that you have people who you're going to engage with, who are leaders in the field, and that is really important in terms of you getting depth and breadth in terms of your subjects and your undergraduate minors, majors, and extended majors. So one measure of quality is what is called the ERA ranking. This is an audit of the quality of research, and it gives you a number between 1 and 5, where 5 is well above world standards, the highest ranking you can get. In the ERA ranking in 2015 and 2018, Monash was one of a small number of departments, physics departments in Australia that received 5s for all of its assessed fields of research, an overall rating of 5, and also the highest rating for the impact of our research. So again, I emphasize that this talks to the quality of the research, and that quality is translated into the undergraduate curriculum, both in the laboratories, the observatories, the computational, the physics and astronomy collaborative learning environment, and so forth. So I would argue that if you're interested in the cosmos or biosciences, environmental sciences, or the fundamental laws of nature, then there are physics and astronomy units at Monash that will suit your interests. Now, I want to talk briefly about teaching and teaching innovations. Monash Physics and Astronomy has put a huge effort, many, many millions of dollars, into improving the environment for our students. So some examples of innovations I've highlighted here, what is called the Lightboard Micro Studio, and this is used to provide engaging, interactive activities between academics and students. And during the current pandemic, this Lightboard has allowed us to literally deliver engaging, interactive activities remotely. So the Lightboard allows us to implement what is called a flipped classroom, where students are provided with all the background material online, and then when they do come in, or in the current climate when they engage through the Lightboard or Zoom sessions or other media, then we value add to the experience they get. We've put money into what is called the PACE Studios. This stands for Physics and Astronomy Collaborative Learning Environment. And these studios are unique in Australia because what we've done is we've abandoned conventional lectures and we've assigned students to small groups working in teams, and this is promoting communication, teamwork, problem solving, and so forth. We've introduced innovations like live programming, problem-based learning, perusal. We have units in indigenous astronomy. We have a unit in Prato in Italy. So we have an astronomy unit called From Galileo to GPS, How Astronomy has Shaped the World. And that's run from our Prato campus. So there are many innovations in teaching and learning. And this really speaks to the fact that Monash Physics and Astronomy is invested not just in research, but in the quality of its teaching and learning programs, and you as a student will be the beneficiary of those. we've developed things like massive online open courses. So these are called MOOCs. And so one developed recently is How to Survive on Mars. These are free. You can go online when these run and sign up for them. And there are many MOOCs available. Here's a series of slides showing our physics and astronomy collaborative learning environment. And I put this up just to show you the kind of environment that you'd be exposed to in first year physics or first year astronomy. And you can see that there are learning spaces, there are breakout spaces, there are areas for students to engage doing laboratory work, doing problem solving, doing mini lectures, doing a whole range of activities within this so-called PACE environment. And this has received a lot of attention both nationally and internationally. And as I said earlier, we're considered leaders in the development of innovative pedagogy, innovative teaching in the context of physics and astronomy. Here's some slides just showing the renovated spaces for our undergraduate teaching at second and third year. So we have things like completely renovated second and third year laboratories, student areas, computational areas, and so forth. And really, this is trying to promote a community of students. And so the top right-hand slide shows students in the student lounge in second and third year. And we've deliberately mixed second and third year so students can talk to higher years. Academic staff wander through this informal area. This is not a formal teaching space, but it's a brilliant space for students to drop in, to work in small groups together, to interact with academic staff and indeed professional and technical staff. And students give a lot of positive feedback about this kind of environment. In fact, it's one of a number of spaces we have within the school that promotes collegiality and a working environment where students can engage with each other. We also have our own observatory, the Hutton-Westfold Observatory. This contains 2 optical telescopes and a radio telescope. Of course, we do significant research in astronomy and astrophysics within the school, but this is part of our undergraduate teaching. I should also point out that because we're doing research in all of the areas that I mentioned from A to Z, students have the opportunity to do projects in any of those areas with academic staff. And this is really important because even if you don't go on to become a professional physicist or a professional astronomer, doing a research project provides you with an opportunity to be creative, to engage with cutting-edge ideas, experiments, equipment. And in many cases, this is done not just with academics within the school, but international, so academics from around the world. So let's just talk about this. We've said that we're promoting an environment where students are learning about how to solve problems, how to communicate, how to work together in teams, and so forth. So let's just talk about the kinds of skills, that the careers that employ students with skills and background in astronomy, astrophysics. So our graduates find employment in a very wide range of areas. And I've just put a list here, and in fact, if you have a look at our brochure, which is also available on the Open Day platform, it lists about 24 careers where our students have found gainful employment. So astronomy and astrophysics, clearly, but biomedical imaging, science communication, working at the Australian synchrotron as a synchrotron scientist, medical physicist, even patent attorney. The world's most famous patent attorney was probably Albert Einstein, because a patent attorney looks at whether a device or a set of ideas can be translated from ideas into something which can be made. So this is a patent attorney. Einstein was a patent clerk. There are many areas in which the skills that you acquire, the analytical skills, the problem-solving skills, the dealing with complex data, empirical reasoning, etc. These are really highly valued by many industries. And of course, we're looking to the future. So what kinds of careers can we expect in the future? Well, without doubt, machine learning and artificial intelligence, big data analytics is going to be one of the amazingly big growth areas. And remarkably, the research that we do within the school in astronomy, in particle physics, in gravitational wave physics, in condensed matter physics, the students are required to understand aspects of machine learning, the ability to handle large amounts of data, to write code that facilitates the analysis of that data and the visualization of that data. And we find that those skills are highly sought after by the finance sector, by a whole range of consulting firms, big consulting firms. And we've been told that those companies will prefer to take someone with a background in physics, astronomy, mathematics, engineering, and then learn by adding on the other technical skills and perhaps economics and finance rather than the other way around. And that's because of the flexibility, the creativity, and the problem-solving skills that you gain as part of a generic background degree in Bachelor of Science with a major in physics or a major in astrophysics. So here's a snapshot of physics and astrophysics employment. You can see a big chunk of this pie diagram is devoted to industry and consulting. And then there's technical and management, commerce, a small percentage of graduates going to secondary teaching, which is a pity because I think we do definitely need passionate and gifted physicists to communicate to the next generation of students their passion and also their understanding of the discipline. With people going to CSIRO, defence, other national laboratories, some go in, become a very small percentage become academics at universities, and so forth. So this is a kind of breakdown, and you can Google careers through the Institute of Physics, the American Physical Society, or the Australian Institute of Physics, and it will give you further background. At the end of this slide, I've got some links that you might care to look at. So let's look at some very specific employment opportunities. So our graduates find employment in diverse areas. So I talk about industry. So what sort of areas? Agilent, Optiscan, Bosch, Amcor, Cyclotech. These are industries that are involved in producing scientific instruments or products such as radiopharmaceuticals or solar cells or a whole range of other industries employ our graduates. Government research labs, CSIRO, the Defence Science and Technology Organisation, the Australian Nuclear Science and Technology Organisation, the Bureau of Meteorology, the Australian Synchrotron, and so forth. In fact, when the Australian Synchrotron was first built, the very first graduates that went into that came from Monash Physics. They became beamline scientists and accelerator physicists. Hospitals, so medical physicists working with oncologists, working with radiographers, radiologists, imaging. This is also an important area. So our graduates find employment in the Austin, the Alfred, the Royal Melbourne, the Royal Prince Alfred, and so forth. They find employment with major consulting companies, principally and increasingly in data analytics, machine learning, complex modeling. This is the sort of thing that physicists are extremely good at doing. And when you learn these skills in one area, they're transportable to another area. I personally have had two of my graduates who did work in fundamental physics, then go in, apply those ideas in the area of climate modeling or in financial modeling or in complex systems. Of course, as I said, a small number of people go into research and teaching in universities or school teachers. Some of us find our way into museums, not as exhibits, but in fact as scientists that are responsible for the production of exhibits in museums, planetariums, and so forth. And as I said, the financial sector, media, management, logistics, and transport. So it's extremely wide. And so the take-home message is, we will provide you at Monash in physics and astronomy with many opportunities in both the engagement with your colleagues, with academic staff, with research projects, with a whole range of things. And if you avail yourself of those opportunities, you'll pick up skills, the so-called metacognitive skills, sometimes disparagingly called the soft skills, and those are really highly valuable. So what industry is interested in is they want to know that someone can solve the Schrödinger equation in quantum mechanics, but they're not going to employ you to do that. They just want to know that you're smart enough to do that, because if you're smart enough to do that, they figure that you can be trained to do other smart things and make that company money. And so these are some of the reasons why our graduates find employment in such a diverse range of industries. So let me now conclude with some a discussion of our research. As I said, Monash Physics and Astronomy has the highest rating for the quality of its research. It's a 5 for all our research programs, and most importantly, we also have the highest rating for the impact of our research. So people can do research, but it may not have as much impact in terms of its societal benefit. So our research is not only fundamentally impactful, but it's also societally impactful. And so there's only a very small number of physics and astronomy departments in Australia who have this kind of ranking. So we have 4 basic themes. I'll go through them and then I'll highlight the kinds of things that you find within. And this will also demonstrate the breadth of the activities that we engage in here at Monash. So I didn't say it, but Monash is one of the largest physics and astronomy departments in the country. So the first theme is called New Windows on the Universe, and this includes observational astronomy, high-energy astrophysics, computational astrophysics, and the brand new field of gravitational wave astronomy, which was born in 2015 with the first detection of the merger of 2 black holes, a binary black hole merger. And we were involved in that fundamental discovery, that fundamental paper that led to the award of Nobel Prize to the 3 people involved, including Kip Thorne, who's a friend and colleague of the department. And that Nobel Prize was awarded in 2017. And so we are very actively engaged in gravitational wave astronomy. And this is also interesting because the kinds of techniques that have been developed to analyze gravitational waves turn out to be extraordinarily useful for industries such as banks. And we've had engagement with banks who want to use these tools and apply them to understand complex financial modeling rather than complex physical modeling. The second theme is called the New Quantum Revolution. Many of you may have missed the old quantum revolution. Well, the old quantum revolution started in the 1920s and went through the 20th century, and that allowed us to understand, at some basic level, the process of quantum physics, the physics of the microscale, what electrons do and why they're so different than what billiard balls do. But the new quantum revolution is an emerging area in the 21st century physics, and this is about not only just understanding the quantum world, but manipulating and therefore being able to generate technologies on the basis of these quantum ideas. And so this covers atomic and molecular condensed matter physics, quantum computing and quantum information theory, ultra-cold gases and quantum metrology, and so forth. Quantum metrology is about measurements, quantum sensors. For example, can you measure the magnetic field associated with a neuron in your brain as you think? The answer is yes, you can, but you need to use a quantum sensor to do that. The third area is the quest for new physics and symmetries. This includes the whole area of particle physics. And so we do have both experimental and theoretical particle physicists within the school, and they're looking at everything from the standard model of particle physics, which was validated just in the last 5 years with the discovery of the Higgs boson, and we were also involved in that discovery, which led to a separate Nobel Prize to Peter Higgs and co. QCD, or quantum chromodynamics, and most importantly, we're looking at physics beyond the standard model, dark matter, dark energy, quantum cosmology, and so forth. So we are involved in theoretical physics as well as experimental physics, using facilities at the Large Hadron Collider, like the CMS experiment or the LHCb experiment. We're also involved in experiments at other laboratories such as JPARC in Japan and so forth. And again, I emphasize that this gives you enormous opportunities to engage not only in research projects, but with world leaders who I think will really fire you up with the passion they have for understanding the world at its fundamental level. And surprisingly, these fundamental ideas, as I've tried to bang on about, translate to technologies. And the last area is the new ways of seeing and understanding the physical world. This obviously includes optics, but you can do optics with not just light. You can use neutrons or electrons or even atoms. There's a whole branch of optics called atom optics, which is a research area also within the school. X-ray and imaging sciences, and of course synchrotron science. So within each of those themes, there is the whole spectrum of individual research areas. I won't go through them, but you can see it does range from A all the way through to X-ray physics. I should put Z there, but it's really encapsulated within particle physics. And these researchers complement it with significant research centres, and I've listed the most important research centres that we're involved in. ARC Centres of Excellence are nationally funded centres with significant investment from the Commonwealth Government. And you can see we have an ARC Centre of Excellence in future low-energy electronics technologies. What is this about? We're trying to reinvent the transistor based on completely new quantum ideas. Why are we doing this? Because we're getting towards the end of what is called Moore's Law, which says that every couple of years you're supposed to double the capacity of a transistor, but you also increase the amount of power that you need to do this kind of computation at a global level. We're trying to break Moore's Law by reinventing the transistor, not based on CMOS, but new quantum technologies such as topological insulators. We're part of the ARC Centre of Excellence in Gravitational Wave Discovery called OSGRAV. And as I said, we were involved in the discovery of gravitational waves, and this is just an incredibly exciting area. Literally every month, discoveries are being made and published, and this is an area where we're very, very active. We've just joined the ARC Centre of Excellence in All-Sky Astrophysics, or Astro 3D. We've been part of the Centre of Excellence in Particle Physics at the terascale. This is the scale of tera-electron volts, because if you look up the operational energy of the Large Hadron Collider, you'll see at the moment it's about 13 TeV, 13 tera-electron volts. Then there are internal centres such as Centre for Astrophysics, Atomically Thin Materials, Centre for Electron Microscopy, and also the Centre for Nanofabrication, which allows you to build nano devices and explore them. And that's a centre that's run jointly with other universities. I should point out that as I said, we've invested significantly in our infrastructure. So this is the New Horizons Research Centre, which was opened up in 2013. And this is a $175 million investment in research infrastructure and equipment. And this houses all of our research facilities. And as a student, you would be doing projects. You could be doing projects with a researcher within the New Horizons Research Centre. It's an extraordinary building. It's got incredible equipment. Again, we have extraordinary facilities. The Australian Synchrotron is literally on our doorstep. It's across the road from where I'm currently speaking, about a 10-minute walk. The Centre for Electron Microscopy has got some of the world's most advanced instrumentation, and this year this instrumentation is going to be upgraded to produce extraordinarily new capabilities. And again, students and staff have access to this. And then there's a Centre for Nanofabrication on the bottom left there. So let me just very quickly go through a few snapshots. As I mentioned, we're trying to reinvent the transistor, the next generation of electronics, photonics, and photovoltaics. So these are a couple of researchers, these are graduate students and a postdoctoral researcher within what is called our Scanning Tunneling Microscopy Laboratory. This is a snapshot with an STM, and this is the surface of silicon. And you notice the scale bar there is 4.4 nanometers. A nanometer is 1/billionth of a meter. So we're actually able to image at atomic resolution the surface of materials. But in fact, you can do more. This facility not only allows you to image these materials, but to manipulate them. You can deposit atom by atom and then image the structures. So this is about developing new kinds of materials for new kinds of electronics. We also produce the coldest stuff in the universe. This is called a Bose-Einstein condensate. How cold? Well, if you cool the air in this room down to about minus 196, it'll turn to a liquid. If you cool it further, it'll turn to a solid. If you take helium and you cool it down to about 270 degrees below zero, it turns to a liquid. So if I flip this on its head, the absolute zero is zero. And helium turns to a liquid at around about 2 or 3 degrees above absolute zero. And this is called 2 or 3 Kelvin. So the current room temperature, we're at about 293 Kelvin, 20 degrees Celsius. So how cold is this stuff? Well, this stuff is about 100 billionths of a degree above absolute zero. It is about as cold as you can get. It's colder than the background of deep space. And why is this interesting? Because it turns out that when you cool atoms down to these temperatures, they undergo a phase transition and change their state. And this transition is a little bit like how water turns from vapor to liquid or from liquid to ice. That's a thermodynamic phase transition. Here, these atoms are turning to a new phase of matter called the Bose-Einstein condensate. And this has got extraordinary interesting properties. If you cool this thing down and you form a gas of these atoms and you let them collide, they don't behave like particles, they behave like quantum waves, and they undergo quantum interference. And you can see in the middle area there, you can see a whole little dots. These are called quantum vortices. So one of the properties of this BEC, this quantum gas, is that it's a superfluid. If you stir it and you stop stirring it, the fluid continues on forever. Unlike an ordinary fluid, if you stir a cup of tea, you take your teaspoon out, very quickly, because of dissipation, the fluid stops. Whereas this fluid continues forever. It's a superfluid. Another property is if you stir your cup of tea, you stir it a little harder, you get a whirlpool. And if you stir it harder and harder and harder, you just get a more violent or a steeper mini hurricane inside your cup of tea. What happens with the BEC is when you stir it, you get a vortex or a whirlpool. But when you stir it a little harder, you get another whirlpool. In other words, the whirlpools or vortices are quantized. So this is another aspect of the quantum state of matter. Now, the question that you can ask is, well, what are we going to do with this? Well, this is a really good question because at the moment we've been able to develop this stuff, but in terms of translating it to new technologies, we're really at the beginning. But one of the things we are looking at is using this to produce what are called atomatronics, using the atom in its entirety rather than just the electron as in electronics, but using the atom to produce a device, an atomatronic device. And these devices have been engineered and explored both fundamentally and practically within the school here. Of course, as I mentioned, we have a very significant number of people involved in astronomy and astrophysics, and we cover a huge range of areas from galaxy evolution through to gravitational wave astronomy. We're involved in a number of major projects such as the Square Kilometre Array, the SKA, the Advanced LIGO, which is detecting gravitational waves, the Large Magellan Telescope, and GOTO, which is a telescope which we've constructed jointly with our partners in the UK. And these telescopes are stationed on the Canary Islands. They're accessed remotely. In fact, students can access these telescopes remotely. And what are these looking for? They're looking for flashes of light associated with violent events in the universe which create gravitational waves. So it's a follow-up to gravitational waves. So we look at gravitational waves with LIGO, and we're doing research that involves LIGO, and then we can do the follow-up with optics using GOTO and other telescopes. As I said, gravitational wave astronomy, the top left-hand shows a picture of the so-called LIGO observatory, the Laser Interferometry Gravitational Observatory at Hanford, Washington, in the US. And I'll just give you an aside. One of our third-year students, as part of a project, spent 6 weeks working at LIGO. In fact, we've had 3 students working at different gravitational wave observatories in the US. The top right-hand side is the famous Parkes telescope, and that's been used for another aspect of gravitational waves. I won't go into it. And the bottom right-hand is the GOTO telescope. It's an array of telescopes which are in the Canary Islands. I'll just finish with a couple of other areas, and by no means does this cover all the things we do, but particle physics and cosmology. We do both experimental and theoretical high-energy particle physics. As I said, we cover the standard model of physics beyond the standard model. We're involved in projects at the Large Hadron Collider, which is called CMS, the Compact Muon Solenoid, which was one of the detectors used to detect the Higgs boson, and LHCb, and the B is a really interesting thing. I'll just get you as a little treat. Do a Google search on LHCb and find out what the B stands for. I'll give you a tantalizing hint. It stands for beauty, and it's not what you think. So have a look at that. And that's another area, and this is looking for physics beyond what we already know, because we know there has to be physics beyond the standard model. Why? Because there's dark matter and dark energy, and that does not fit into the standard model. So what is it? So that's one of the things we're looking at. We have very significant research input here. We also work with partners in Japan, Europe, the UK, and the US. let me finish with some comments about biomedical imaging, just to highlight how some of the fundamental ideas that we've discovered have been translated into practical applications involving clinical practice. So here is one of our researchers, Dr. Kay Morgan, who's a future fellow in the school, and she is a pioneer in what is called phase contrast imaging, or X-ray phase contrast imaging. The bottom right is the Australian synchrotron, where she's doing experiments, and the top right is the big synchrotron in Japan, where we have a unique arrangement with the Spring 8 synchrotron in Japan, which allows us to access this facility on a regular basis. So what is phase contrast X-ray imaging? Well, basically, you all know what X-rays are. You've had an X-ray radiograph. If you break a bone, you can get a radiograph, or you have a CT scan. No matter how the image is produced, what it does is it's based on how X-rays are absorbed or how they're scattered. But X-rays do other things. They bend as they go from air into, say, human tissue, in the same way as light bends when it goes from air into glass, air into water. Tantalizingly, it bends the opposite to how light bends. But why this is important is because this bending or refraction produces contrast, which allows you to image biological structures with high resolution that you can't do using PET scanning or NMR or MRI scanning or CT scanning. So it allows you to image, for example, the lung. And this has allowed us to understand such fundamental questions as how does a newborn baby clear fluid from its lung at birth? Or if a baby's delivered in a compromised scenario or preterm or by cesarean section, what are the ramifications? And the work that we've done in phase contrast imaging, clearly not on newborn babies, but on animal models, have allowed us to translate those insights, those unique insights which are only afforded by X-ray phase contrast imaging, into clinical practice, which has actually saved lives. It's been used as protocols in hospitals for how to treat newborn babies with compromised respiratory function. So on the top right-hand side, you can see here's the lungs, the ribs. This is actually a rabbit. And you can see the kinds of images you can produce with this new technology, which was developed here at Monash in concert with our partners at a number of other universities, but we had very significant input. In fact, I would argue that our input into this whole field has been probably the most significant in the country. Okay, so let me conclude. I've talked a little bit about why you may want to consider, I think you should, why you may want to consider doing physics and astronomy. I've highlighted that it's a fantastic time to do physics and astronomy. There's so much that's waiting to be discovered. We're just at the beginning. People often think that we've discovered everything. We've discovered very little, and we've got so much to do. We've discovered very little? Well, here's a fact. About 5% of the observable universe is stuff like you and me. It's called baryonic matter. Electrons, protons, neutrons. Actually, strictly, electrons are not baryons, but you can look that up. In any case, 5%, where's the other 95%? Well, we don't know. We know that there has to be dark matter and dark energy, and that comprises the other 95%. We don't even know what it is. Maybe you will be the person who discovers what this is, and if you do so, you can book your passage to Stockholm because it's a Nobel Prize. So no matter what area you look at, whether it be new quantum materials, ultra-cold gases, condensed matter physics, new techniques in imaging, taking data analysis tools and applying them to completely diverse areas, such as understanding the functioning of the brain, sensitive measurements, across the entire spectrum, there's good reasons to do physics, and I would argue that because we do cover the entire spectrum, there's good reasons for you to consider coming to Monash to do physics. We'd love to welcome you to Monash. We'd love to have you engage with our staff and other students and become part of the community of physicists and astronomers that have been generated through Monash over the last many, many decades. So thank you virtually, and I look forward to answering some of your questions on the online platform in Open Day. Thank you.